Welcome to qnawire.
In this question, we have a capacitor network between points A and B. So it looks like this. Okay, it's just two capacitors in series. Okay, and then the two capacitors, they are 150 nanofarad and 120 nanofarad. Okay, and it's connected to a battery, okay, of 48 volts. Okay. Right, so there are 5 parts in this question. Okay, first we need to find the total charge in the network, and then the total charge on each capacitor, the total energy stored in the network, the energy stored in each capacitor, and the PD, potential difference across each capacitor. Okay, so to find the charge stored in the system, we first calculate the equivalent capacitance. So for capacitors in series, it will be 1 over C1 plus 1 over C2, and then you take the reciprocal. Okay, and then you just 150 plus 101 over 120, okay, and take the reciprocal, and the final will be in nanofarad, and this is 66.7 nanofarad. Okay, and then the charge stored would be C equivalent times VAB. Okay, so 66.7 times 10 to the negative 9 times 48. Okay, you calculate this, you get 3.2 microcoulomb. Okay, then in part B, the charge stored in each capacitor. Okay, so I'm going to call C1 is 150 nanofarad, and then C2 is 120 nanofarad. Okay, I'm going to use this C1 and C2 from now on. And then the charge, since the two capacitors are in series, the charge stored in C1 is equal to the charge stored in C2. Okay, and they are also equal to the charge stored in the system. Okay. Okay, which is 3.2 microcoulomb. Okay. Okay, in part C, we want to find the total energy stored in the network. So, total energy stored. Okay, we'll be using the formula half C equivalent times VAB square. Okay, it's basically half CV square. Is that we use equivalent capacitance, okay, instead of the individual capacitance, okay, times 66.7 times 10 to the negative 9, and then VAB is 48 and square. Calculate this, you get 76.8 microjoules. Okay, next we will find the energy stored in each capacitor. Okay, so the energy stored in C1, okay, then we will use half Q square over C1, okay. Yeah, because the Q are the same for both capacitors, so using this version of the formula makes it very easy to calculate the energy stored, okay. So you just substitute the numbers. Okay, you calculate this, you get 34.1 microjoules. Okay, so this is a 150 nanofarad capacitor. Okay, next we calculate the energy stored in C2. Yeah, I'm just going to write it as U2. It's half Q square over C2. Okay, and half and 3.6 times 10 to the negative 6 square divided by 120 times 10 to the negative 9. Okay, calculate this, you get 42.7 microjoules. Okay, so you can see that these two numbers, 34.1 and 42.7, they add up to 76.8, which is the answer in part C. Okay, and that makes sense. Okay, in part E, we want to find the potential difference across each capacitor. So we can use V1, because we'll be using the formula Q equals to CV, right? So V1 is Q over C1. Okay, so this is for the 150 nanofarad capacitor. Okay, calculate this, you get 21.3 volts. And then for part, then V2, just repeat Q over C2, 3.2 times 10 to the negative 6 divided by 120 times 10 to the negative 9. Sorry. Right, so you get 26.7 volts. All right. So again, these two numbers, they add up, should give you 48. Okay, which says that the voltage is shared by the components in the circuit. Okay, and that's all.